In this video, we will discuss the VMAX 4000 model 4030 NVH input module. To begin, I'm going to navigate to the System Setup panel and then to NVH channels. The 4030 NVH input module has 6 BNC connectors on its face and can accept up to 6 high-speed NVH channels. This module is unique compared to the other input modules in that it collects and samples data at 51.2 kilohertz, so 51,200 samples per second. Now it's worth mentioning that the NVH input module collects FFT-based data, so we are strictly looking at frequency-based data coming from the 4030 NVH module. There are ways to collect some time-based data either through audio files, through WAV or MP3, as well as we do have a software add-in that will allow an NVH channel to be collected as an analog input channel, but you are limited to the base sampling frequency of 1000 Hertz. So to begin, I will show how to set up a couple of different NVH channels. And we're going to start off by going to the table sort of in the upper right-hand corner here. Right now, all of my channels are turned off. And currently, my ICP or my IEPE power supply is also turned off. Now, the couple of different sensors that I'm going to use today typically do require ICP or IEPE power supply to be turned on. So I'm going to start by first selecting the type of channel that I would like to collect. So I'm going to start off with a wheel microphone. And you'll notice when I select that, it does change my channel status to being logged. Currently, my IEPE power supply is not turned on. I'm going to go ahead and turn that on. And when I do that, the little LED next to channel 1 will light up green if I have a sensor that is plugged in and it's within a specified voltage range of the IEPE power supply. And if I disconnect that, I will actually see an LED turn red, indicating that there is an issue on this particular channel. Now to start off, I should note that this microphone that I'm using is a B&K microphone that does have TEDS capability. And TEDS allows us to access serial number, model, as well as calibration information that is stored directly on the transducer. So in this case, over on the left-hand portion of the screen, down here is where we would typically perform our calibrations. If I click the Query TEDS from Device button, you will notice that I get all of this information that has been supplied down here. I can see the last date it was calibrated. I can see the sensitivity values. And if I go into this sensitivity box here and I use the Use TEDS button, it will bring in this information for me. And now I see that the sensitivity cal channel 1 button is flashing yellow. I can go ahead and click that. Now upon doing that, this channel has been calibrated. Now if I whistle or make a high frequency noise here, we should be able to see that in the live screen that we're looking at. So you can see somewhere around 2000 Hertz, I have a peak frequency there from me whistling. So now that I have a signal that's working, I do want to look at what I have my full scale set to. So currently the full scale is set to 114 dB. If I would like to set this higher, I can do that in this table here by typing, or I can do it down in this sensitivity field as well. So if I needed to have my full scale set to like 130 dB, for example, typing that value in, hitting enter, now you'll see my sensitivity cal has lit up. And if we pay attention to this gain setting of 23 dB, we should see that also change as I click the calibrate button. Now after I've done that, you'll see my full scale has changed, and then my gain setting has also been turned down some. Some of the other columns that we have in this table here, after we've selected our channel, we can change the unit, whether that is collected in dB or G for an accelerometer, for example. I discussed already the IEPE or the ICP, which is a constant current DC voltage supply. There's also this high pass filter, which does, if turned on, gives us the ability to apply a 100 hertz filter that is intended to help filter out wind noise when the windows of the vehicle are down while driving. There's also A, B, and C weighting scales that can be selected on a channel-by-channel basis. And then we also have over here the ability to look at our frequency, our resolution. So currently we are set up with 800 lines from 0 to 20,000 hertz, meaning that each frequency bucket is 25 hertz wide. Now, we do have the ability to get better resolution, but doing so is going to reduce the maximum frequency that we can sample up to. So for example, if I enter a number here larger than 1, you'll see that my frequency divisors is now set to 5, and I now have 5 hertz resolution. Every 5 hertz I have a unique bucket. But my maximum frequency now is limited to 4,000 hertz. Now this is with our FFT lines of resolution set to 800. There are a lot of different options in this table, as you can see. We can go up much higher than that. We could go all the way up to 8192. Now in doing that, we will notice that it takes more time to sample in order to be able to take those measurements. If I go back to a frequency divisor of 1, now you can see I can actually go up to 25.6 kilohertz with a little over 3 hertz resolution. Now for our standard brake squeal noise detection, 800 lines, 0 to 20,000 hertz, and 25 hertz buckets is the most common setting that we currently use. Okay, next I'm going to set up a accelerometer. So on channel 2 here, let's just select right front accel, or maybe let's go ahead and freeform type a new name for that one, just to show how that functionality works. So I've turned this channel on. This is the description of it. Units I want to be in G. Okay, I'm going to turn on my ICP supply. I do not need this wind noise filter on this accelerometer. And I want to have my full scale on this one set pretty high because I'm going to be driving around on bumpy roads and I don't want this channel to saturate while I'm taking a noise measurement. So I'm going to set this to, say, 100 G. Okay, so now to do calibration work, I want to go down to this channel 2, Excel number 1 here, field. And I could use a calibrator. I don't currently have a calibrator with me, and the calibrator typically would shake the accelerometer at 159 hertz at 1 G. Alternatively, I can use a sensitivity value, and the accelerometer that I'm using is a 10 millivolt per G output, and I'm going to scale this to be 100 G full scale. So you'll notice as I've hit enter inside of one of these fields, it's going to notice that there's been a change, and it's going to ask me to click the calibrate button. So when I click the calibrate button, now you can see that this gain updated here, and we can look at if I'm actually collecting any data in our live screen here. So I have a function generator that I'm using right now to supply a D voltage going in at a specific frequency. If I provide some additional amplitude, we can see the signal grow. And then I can also change that frequency. And we can see that we can go very high in the frequency range. So I'm currently outputting a signal at about 19,000 hertz with an amplitude of 75 G as indicated here. Now, in addition to setting up these channels and calibrating them, you'll notice that we have a lot of options over here on the left side of the screen for our FFT Spectral Settings, frequency range, waterfall, and audio file as well. So we talked a little bit about the FFT lines of resolution already. This is going to define how many buckets that we have inside of the frequency range that we're working with. Again, 800 lines up to 20,000 hertz is very common for what we do. Then there are also some settings for overlap, so no overlap all the way up to 67%. Then looking at what type of spectrum we want to collect. No spectrum, I've never used this one before, but waterfall, where we take multiple FFTs throughout the course of an event, or simply a like peak of all spectrums, which would be one per event. And then there are a couple of different peak modes, so peak or averaging. There are also different windows that can be applied, so Hanning, Hamming, Blackman, et al., or none. And I'm kind of sticking with our current defaults that we use for our brake squeal noise testing. And then we can also collect audio files as well. So I mentioned before the ability to take some time-based type data. So generally used for reference when we want to listen to a microphone or listen to an accelerometer to hear exactly what was going on. We can do that based against time, and we have a few different options. We can collect wave files, MP3 files, and DVR files. MP3 files at 128K is the typical setup for us. And the threshold that we see here, typically I want to set this to be very low, such that any time that the microphone sees more than 1 dB, we will collect audio files, which essentially is going to mean we are always going to collect MP3 files. I prefer to always have them, and then we can always be discarded later on if required. Okay, in addition to those settings, over here for the frequency range, when we have waterfall data turned on, we can set that up to be similar to where we only save waterfall if we see a peak decibel level above a certain level. Now again, I always want to have waterfall data saved. And waterfall data means essentially when we have more than one FFT collected throughout the event. In this case, we are looking for the frequency range between 1 and 20,000 hertz. When we exceed 1 dB, we will save waterfall data. Now, the frequency range that we see here, this does not at all dictate what we are logging data as or anything like that. This is really just used for making this determination on whether we save waterfall data or not. And when we do save waterfall data, over here in this drop-down for spectrums per second, this allows us to dictate how many wave spectrums or how many individual FFT plots are we going to collect per second. So in the case of 1.00, this would be every 1 second we will have a new FFT to look at. We can go as high as 50 spectrums per second. Now, the higher you go here, the more intense and the larger file sizes you are going to have. So setting this to 50 spectrums per second, may sound great to have really good resolution on exactly when a noise event happened. It may not be practical depending upon the type of testing that you're doing. 5 wave spectrums per second, generally speaking, for the testing that Link does, this has been pretty sufficient for most of our testing. This will provide a new FFT every 0.2 of a second. You still have all of the data in between those 0.2 of a second. They are just saved as a peak between those points. So it's not like you're going to miss a noise event happening. It's just when it does happen, you would know within plus or minus 0.2 seconds when that actually occurred. So now that we have this set up, I'd like to go ahead and log an event or two so that we can look at how the NVH data is collected. So I'm going to turn my logger on, and I'm going to manually start logging by hitting the space bar. I'm going to whistle into this microphone, and I'm going to provide a little bit of amplitude to the second channel with the accelerometer using my function generator here. And then I'm going to go ahead and turn my logger back off. So if I open RevData Plus, which is the software that we use to analyze our data that's been collected, I'm going to go ahead and look and see under section 1 here, stop number 8 is where I collected that NVH data. And to look at that data, I've got a few different buttons up here, radio buttons that can be used. The first one would be for my audio files. So if I click on that button here, I will see that I have 2 separate MP3 files that were collected. Now if I check this button here, I'll actually be able to see what that time signal looks like. So in addition to the audio data that we've collected, I can click on this button here, which is going to show a spectral data summary graph. And there's really not a whole lot for us to look at here, but we can see that right now I'm looking at the peak of all spectrums. So this would take the entire event that I took and take the peak at every single 25 hertz interval that we're looking at for both the microphone and the accelerometer. And if I use my right mouse arrow, or my right arrow key, I can go through the individual FFTs. You'll notice that each time I increment a new spectrum, it's going to advance 0.2 of a second. Remember the 5 spectrums per second that we programmed in. So we'll see that I have a peak in frequency on my accelerometer, and then at some point when I'm whistling, we'll actually see that being reflected as well. So we can see that here. In addition to that, there's also this spectral graph, and if I bring those over, what we will see here is that we have a unique FFT every 0.2 of a second, and it's displayed in a little bit more of a 3D type of arrangement for us to look at. Something that's kind of interesting is that if I move these around on the screen a little bit, and I click play, you can see that we're playing through the audio data as well as it's actually panning through our spectral data that we have in 3D here. Now, if I also pulled up a raw data graph, and I really don't have any raw channels that are necessarily being collected that are meaningful, but I click play on that also, you'll see that we also pan through where we are at in our raw data. If I were to grab this and slide back and forth, you'll see that that's interactive in all of the different windows. If I had one of our video sensors connected as well, I'd be able to do this same thing with video. So I'd also mentioned that there's a way to take our NVH data and actually collect that as a time-based signal. In order to do that, I would need to go to the add-ins section of the software, and I would need to make sure that under audio, I have this NVH as AIN add-in installed. Now, if it's not installed already, you'd be able to find that in your available down here. You could select it, click the install selected add-in button, and it would reboot the software, installing that software add-in for you. If I double click it and go into this add-in, you'll see that any of the NVH channels that I currently have installed on the machine would be available here. And I can turn those on and off, and I can now take a sampling of those at my standard logger rate, which right now is limited to 1,000 hertz. So this could be useful for looking at lower frequency type of resolution on something possibly. Maybe we want to look at when we hit bumps in the road, we actually want to be able to see an acceleration based upon time. You wouldn't really technically use this for frequency analysis. Our NVH tools are better suited for that. But for having an analog reference to one of your NVH channels, this gives you a way to do that just by installing a piece of software. Now in the same data set that we just collected FFT based, where I used my function generator and then I actually provided some change in the amplitude, this is what that result looks like when I'm looking at that as an actual analog channel. So this is being collected at 1000 Hertz, and we can see the actual time-based data here. This concludes our video on NVH setup and calibration. Thank you for watching.